India's 2024 general election involves 970 million eligible voters. To put that in perspective, that's more than 10% of the entire global population, all participating in a single democratic exercise. Reaching every one of those voters requires setting up over 1 million polling stations. Election officials transport voting machines on horseback to the foothills of the Himalayas and by boat into remote river deltas to ensure total geographic coverage. Despite managing this massive logistical operation, the system has faced intense scrutiny. In the lead-up to the election, the Supreme Court of India heard a series of petitions, demanding either a total return to the old paper ballot system or a 100% manual recount of all printed voting slips. The core argument from the petitioners was straightforward. They claim the electronic voting machines are vulnerable to hacking, pre-programming, and unseen digital manipulation. In April 2024, the court delivered a definitive verdict, dismissing the petitions entirely. They rejected both the return to paper ballots and the demand for absolute manual counting. Making sense of the court's ruling means stepping away from the political rhetoric. Instead, we have to look directly at how these voting machines are engineered and the brutal mathematical reality of trying to count nearly 1 billion votes. The Indian voting setup relies on 3 physical components. There is the ballot unit, which acts as a simple keypad, the control unit, kept by the polling officer, and the VVPAT, a machine that prints a physical paper receipt of the vote. To address hacking concerns, the hardware is built with strict physical isolation. The machines are completely standalone. They have no internet connection, no Bluetooth capability, and 0 external communication ports. Inside each unit is a one-time programmable memory chip. Once the code is burned into this chip at the factory, it becomes impossible to overwrite. More importantly, these chips are manufactured to be completely candidate agnostic. The machines have no idea which button belongs to which candidate. That information is only assigned during the symbol loading process, happening just days before the actual poll in the presence of political representatives. Because the button assignments vary by constituency and happen so late, proactive digital tampering is locked out. When a vote is cast, the VVPAT machine prints a paper slip displaying the chosen candidate. A glass window illuminates for exactly 7 seconds, allowing the voter to visually confirm their choice. The slip is then cut and dropped into a sealed box. You get to verify the vote, but you never physically touch the paper. The security architecture here does not rely on complex software firewalls. It relies on physical hardware isolation and a late-stage, randomized configuration process. Still, if the technology is secure, you might wonder why the Supreme Court didn't just mandate a manual count of every single paper slip to guarantee absolute public trust. The answer lies in the physical properties of the paper itself. The VVPAT prints on thermal paper, coated with a chemical to retain ink. It is soft, sticky, and difficult to handle quickly. Counting the slips for one single polling booth takes a team up to 5 hours. This bar chart shows the projected time and manpower required for different counting methods. The current system verifies slips from 5 randomly selected machines per constituency. If you extrapolate that 5-hour manual counting process across over 1 million polling booths, the 100% column breaks the scale. It would require doubling the election workforce and delay national results by days. India abandoned the old paper ballot system for a specific reason. Manually handling tens of millions of physical papers inevitably led to disputes over smeared ink, invalid votes, and deliberate counting errors. In the past, organized groups could physically take over a polling station and stuff thousands of forged paper ballots into the boxes in minutes. This was a practice known as booth capturing. The electronic machines are programmed to only accept 4 votes per minute. That mathematical bottleneck makes mass vote stuffing virtually impossible. In its ruling, the court recognized that returning to widespread manual counting wouldn't actually increase transparency. It would reintroduce the exact human errors and deliberate mischief that the electronic architecture was engineered to eliminate. This data visualization shows the results of cross-verifying electronic votes with printed paper slips. Over 40 million individual VVPAT slips have been manually counted and checked against the machine tallies to date. Out of all those checks, there have been 0 systemic mismatches. The only recorded discrepancy in that massive dataset occurred in a single booth during the 2019 elections. An investigation revealed that the presiding officer simply forgot to delete the test data from a morning mock poll before opening the booth to the public. The hardware functioned perfectly. The human operator made a mistake. To continue building public trust without grinding the election to a halt, the court ordered 2 new physical safeguards. First, the simple loading units, the laptops used to assign candidates to the machines, must now be sealed and securely stored in strong rooms for 45 days after the election results are declared. Second, if a candidate finishes in second or third place, they now have the legal right to request a post-election audit of the machine's microcontroller. A team of engineers from the manufacturing companies will physically inspect the chips for any signs of tampering, provided the request is made within 7 days of the result. The Supreme Court concluded that a healthy democracy requires transparency, but blindly distrusting established technology only breeds unwarranted skepticism among voters. True security demands verifiable architecture, not continuous suspicion. Securing an election of nearly 1 billion people does not happen by reverting to the manual vulnerabilities of the 20th century. It is achieved by trusting a closed-loop engineering system, backed by strict protocols and the unforgiving rules of mathematics.